thanks Tony, and thanks Linda for the invitation, and thank you for coming. Okay, so let me start with a little bit of motivation here. So the motivation here is in enumerative geometry, and more specifically tropical curve counting techniques. For the enumerative geometry of toric varieties. So I don't want to spend a great deal of time on the specifics of how these things work, but I'll give you a flavor. So roughly speaking, classical enumerative geometry concerns itself with studying Riemann surfaces and how they embed into, let's say, projective space, or whenever I say toric variety, feel free to think projective space or products of projective space or whatever makes you comfortable. And I want these to satisfy some fixed numerical conditions. So I want to fix the genus. I want to fix the degree, the cohomology class. And I want to fix some geometric constraints. So passing through points, tangency to lines, so on and so forth. And the new one, which I'll just put a little star here, is contact conditions, contact orders. Okay, so I'll say words. What do I mean by this? Well, when one talks about usual geometric constraints, what we generally mean is you fix some marked points on the source curve, and then you ask that at this marked point, the image of your curve passes through a variety that's point radial to some cohomology class that represents some cohomology class. The contact orders are essentially this, except that one wants to study fixed contact orders along the toric boundary. Okay? So if you're really interested in enumerative geometry of, say, projective space, you can still do this, just fix generic contact orders along the toric boundary. But I also want to allow things like tangency to the first hyperplane, and triple tangency to the second hyperplane, and transverse contact to the third hyperplane in P2, for instance. The thing I want to point out is that this is fixed. Okay, so everything that I say, this is fixed. This has to be fixed throughout my family. Okay. So what does tropical geometry tell us? Somehow there should be some form of correspondence with counting objects like this and counting piecewise linear versions of them, some form of, these are called tropical curves, embedded tropical curves. And I want to count these inside a vector space. Okay, so what do these look like? Well, they're graphs, for one. They have some unbounded edges, some half legs. They're metric objects, so I want the graphs to have, so each of these edges comes with a length. It's embedded in a vector space with some piecewise linear structure. So each edge has a well-defined integral edge direction. And the first Betty number of the graph, okay, so genus is first Betty number of the graph. There's a good way to define degree here. There's a good way to define what it means to have geometric constraints. One basically just translates the geometric constraints on the classical side. For instance, if you wanted your curves on this side to pass through points, you would want your graphs on this side to pass through points. Okay. A statement like this, A not precise, and B, even if I try to make it precise, can't be true in this generality. I should mention that, so the first results, strikingly, were proved by Mikalkin when he proved this for severity degrees of toric surfaces. So in particular, what did he prove? He said that the severity degrees of toric surfaces, meaning just genus G curves of a fixed degree in P2 passing through points, only point conditions, these were equal to the number of graphs of that same genus, of that same degree, passing through the same number of points. But the graphs on the tropical side are always counted with multiplicity. Okay, so this is not a bijection, but there's a correspondence. And these multiplicities are at the heart of actually figuring out what's going on. They're quite mysterious, or they're starting to become less mysterious, but they are still quite mysterious. So this was extended in beautiful work by Nishino and Siebert some years later. So they were able to do genus zero curves. So they had to weaken the hypothesis, but in arbitrary toric varieties. So, I don't know, quasi-generalization? Okay, yeah. So there's some other instances of this. Cavalieri, Markvig, and Paul Johnson, this was in 2008, they studied the situation for Hurwitz numbers, which you can think of as the enumerative geometry of P1. Enumerative geometry of target curves. So I split these up because the technique. Okay, so first of all, they don't precisely. No one precisely contains the other. This was proved using patchworking techniques, Vero's patchworking techniques. This was proved using logarithmic deformation theory and toric degenerations. And this was proved using the representation theory of Sn, which is ultimately what Hurwitz numbers are. There's some object in the class algebra of the symmetric group, so you can use representation theory of Sn. And hopefully I don't have to convince you that real algebraic geometry patchworking techniques are very different from log, at least on the surface, from log deformation theory. Certainly very different from representation theory of the symmetric group. So at least for me, goal number one, as part of my motivation, is I want some sort of unification of these proofs. And of course, this tends to happen when you unify them. You can understand it from some more conceptual standpoint. Maybe you stand to gain generalizations. Okay. My second motivation is, I guess, partially aesthetic, but partially philosophical. So generally, I've set up some algebraic to tropical curve counting correspondence. But in algebraic geometry, at least for the last 20 years now, much longer probably, how do you actually count algebraic curves? Well, you form some modular space of algebraic objects, some algebraic modular space of sheaves, of curves, of maps, of whatever you might have. For me, these will always be stable maps, but it turns out that these polyhedral objects, these tropical curves, they always, very often, their collections of these are parameterized by polyhedral objects themselves. These are tropical polyhedral complexes, tropical spaces. And I would, rather than having this number equals that number, I would much rather have some strong correspondence at the level of the modular spaces. I want to understand how do families of algebraic, let's say, stable maps correspond to families of tropical maps or families of tropical curves. I really want to understand that correspondence, and I hope, and this ends up being true, is that these guys are actually simple corollaries of that. So there have been suggestions since the very early days of tropical geometry that something like this should be true, that tropical geometry should be viewed as a generalized degeneration technique in Gromov-Witten theory, and I guess essentially some meta result that is based on all of this, all of the work that I'll talk about today, is that 1, 2, and 3 So these tropical curve counts are instances of logarithmic Gromov invariance. Okay, so in some sense we've made precise this slogan that tropical curve counting is logarithmic curve counting. Tropical curve counting, tropical curve counts are logarithmic Gromov invariance. Okay, I will explain what logarithmic geometry is and all of that. But to understand the relationship, I need to introduce another player into this game. Tropicalization and its grown-up cousin, Berkovich spaces, Berkovich analytification. Okay. So the goal here is to somehow do geometry over non-Archimedean fields, valued fields. Okay. So there's two examples that I really like to keep in mind, and if you want to keep those in mind, feel free. I like to think of the trivially valued complex numbers. That's a perfectly good non-Archimedean field, complete non-Archimedean field. It has the discrete topology. Or I would like you to think about the Hahn series field. So what is this? This is some very, very large extension of the Laurent series. Some even larger extension than the Puissant. Okay, so these are series such that the support of the terms is well ordered, and the exponents come out of the rails.
What's the valuation for this stays on this C?
It's trivial. So C goes to 0 infinity, where anything non-zero goes to 0, and anything that is 0, meaning 0 itself, goes to 0. Yeah, it's a surprisingly non-trivial. Yeah, trivial valuation can be surprisingly non-trivial. Such is the way of things. Okay, so now here's what I want to do. Right, so this field comes with the topology, just like the complex numbers. When you think about them as the complex plane with Euclidean topology, this field comes with a topology. It comes with a metric coming from the valuation, and I want to somehow do analysis simultaneously as doing geometry with respect to that metric. So given a scheme, X over such a field, I want some associated analytic object, right? Just like if I have a complex algebraic variety, I can think about it as a complex analytic space, if it's smooth as a complex manifold. I want to do the same thing with respect to this non-Archimedean field instead. I'll explain why later on, but let's, I will explain. The analytification is defined as follows. Okay, so how do you think of the scheme X itself? Well, tautologically, the scheme X consists of those points of X that are valued in various fields of X, various fields. So they're maps from spec K into X, or if you like, if X is affine, it's a map from the coordinate ring of X into some field. But that field is allowed to vary. But that field, in algebraic geometry, that field doesn't keep track of the topology on the space. And I want to just add that as extra information. So X analytic is going to be pairs of little x, comma, valuation, sub little x, such that X is a scheme theoretic point, not just a closed point, close points turn out to be surprisingly boring. So little x is a scheme theoretic point, and the valuation of x is a valuation on the function field. Okay, but obviously I want to respect the valuation on the field that I started with, such that this is, my apologies, with valuation new. Okay, so that's it as a set.
Why did you just take field valued points?
Why didn't I just take the, sorry?
No, why did you just take only field valued points? Why not take all the points valued in any ring or in any K algebra?
Well, what I want to say, okay, so first of all, the answer is that I have to put an equivalence relation here. Once I put the equivalence, I'll tell you what the equivalence relation is. Once I put the equivalence relation on there, I could do this and you could do your thing, but we would end up with the same object, and your equivalence relation would be more complicated than mine. So you can do that, I just won't.
Okay.
Okay, so what's the equivalence relation? It's the same thing you're used to. Okay, so what's the equivalence relation for points in A1C, or A1? It's that if I think of A1 and the number 3 thought of as a real number and 3 thought of as a complex number are supposed to be the same point. Okay, so it's the same thing. If I have a scheme theoretic point, if I want two such pairs to be identified, well, certainly the scheme theoretic points have to be identified, and then both field. So that will put both residue fields into some larger residue field with a valuation on that, such that it restricts to the right one on both. So it's the same equivalence relation that you're used to from scheme theory. It's just that you keep track of the valuation as well along the way. Okay, so I won't write that. Okay, good. So that's just as a set. Okay.
What do you get if you do this to C with the trivial valuation? What do you get if you do this to C with the trivial valuation?
So let me just. Oh yeah, how about I tell you the topology, and then it'll be easier for me to explain that. So I'll put a pin in that for a second. So let me tell you how to topologize this thing. Okay, so let's say X is spec A. This is some K algebra. It turns out that if you think a little bit about this, what this means is that so a point, let's say X comma val X, sitting inside Berkovich space. Right? So this is going to give me a valuation on A to R union infinity. It's actually equivalent data. Okay? It actually turns out to be equivalent data. By the way, a ring valuation is just like what a valuation is on a field. It's just allowed to have a kernel. So lots of things can have size 0. Lots of things can have valuation infinity, not just 0. But other than that, it's the same. Okay, so this is my point. X comma val X. It's not so hard to see that these are equivalent, right? Because the inverse image of infinity is going to be a prime ideal. It's the prime ideal that you want to have as the underlying scheme to any point. So X analytic is now just a collection of these. Just valuations on ring valuations on A that restrict to the right valuation on the field. No equivalence there necessary. Right, so I have a bunch of different functions on this set. Right? For every f in A, I get an evaluation function. Right? These are a bunch of ways to tell me what the size of a function is, up to some kernel. So it's a bunch of ways to tell me the size of a function. So take your way of telling me the size of your function and evaluate that by f. So this is val x goes to val x of f. So what's the topology? Well, in any reasonable world, these things should be continuous. So give X analytic the coarsest topology such that these are continuous. Right? But okay, so this might seem a little abstract. The right way to think about this is that you're sort of pulling back the topology in a natural way from R union infinity. By the way, this R union infinity is the right-hand side compactified. It's with its order topology, not the one-point compactification. Right, so this is how we're putting a topology on X analytic, is we're modeling it on the topology of the real numbers. Now, the real numbers, or the extended real numbers, they have really good topology, and that plays a role here. Okay, so let me answer your question about what happens for A1 with the trivial valuation. So A1C with the trivial valuation I can analytify. Well, here's a bunch of different valuations. Okay. A1 has one point that's scheme theoretic but not closed. Right? So it has the generic point corresponding to the ideal 0. And then I just have all of the complex numbers out. And they will be in their natural topology. So they'll be just a discrete set at infinity. And now the question is, what valuations can you put on the residue field here? The residue field here is just the fraction field of my polynomial range. So I'm thinking A1 is KT. Okay, so here's one of them. You can take a polynomial and you can take suprema. You can take the supremum of that polynomial in an open ball around the origin of various radii. Okay? So radii belong to the real numbers. And it turns out that what this will do is it will connect. So by varying the radius, you will connect this point to all of the points at infinity. And thus spread out the generic point. And where does this ray go? Well, this is varying radius along what center? Along this center. Okay? So that's what it looks like for A1. It's a sort of infinitely branching tree. So the topology around 0, so this is not quite glued from, it's not quite glued from these rays. You can visualize it that way. It's really an inverse limit over finite subgraphs. So there's some Zariski topology, some cofinite topology happening here. Huh?
Is it actually an R tree?
Yeah, it's modeled on an R tree.
It's a what?
R3.
An R tree.
What's an R tree?
It's the right way to say it. It's like it looks like this locally uncountably branching graph with a metric space that happens to be locally modeled on an uncountably branching graph, or uncountably branching tree.
That's the identification
Of A1.
Pardon?
Of A1.
Of A1 over just the complex number.
Over the complex numbers
With the trivial
with the
valuation.
trivial valuation.
Would you also tell us what happens if we start with A1 over the
Non-trivial valuation?
non-
Sure. So it look very
the
similar.
economical brain?
So let me say non-trivial in yellow. The only difference will be that at every point, I can have an additional family of valuations that looks like A1 over the trivial valuation. So it'll be like this, except at every point, I'll do a one-step recursion. I'll take this picture, Control C, when I click on this point, and Control V, and I do this for all the points, except at infinity. So that's what it looks like. But it's still contractible. Oh.
That's what you get for the nautical field?
For the what?
For the nautical field.
The nautical field?
Yeah.
You get this one-time iteration.
Yes.
Successive iteration.
So it's complicated, but it is explicit. It is completely explicit. I can write down all the valuations this way.
Is the contractibility of this related to the contractibility of A1? I mean, is it?
Yeah, but here's the funny thing. GM analytic is also contractible. So this is supposed to be the algebraic torus, right? But it's also contractible. Okay, So this is both helpful and hurtful. It depends. Okay, so GM analytic is contractible, but okay, so there's a good theory of étale cohomology here and a good theory of étale fundamental group. And so étale fundamental group is non-trivial. But you have to dig inside the structure sheet to see the non-trivial topology. But okay, I mean, scheme theory we're used to that. So. Okay, fun. All right, so let me tell you what you actually gain from all this.
Why should I think of this as an analytification or something? It doesn't look like
just a moment. Here, to work with it. Okay, so X has, so this is, it's written last in my notes, but I'll put you out of your misery and tell you the answer now. So X has a structure sheet of analytic functions, locally given by limits of algebraic functions, rational functions. Right, so there's a good notion of analytic function in this world. That's the point. So it's not analytic in the complex analytic sense. It certainly doesn't look that way, as you pointed out. But it does have a good theory of analytic space, of analytic function.
So it's analytic as in chaotic analytic?
Yes. So
it's
yeah,
non-Archimedean.
It's non-Archimedean analytic. Yeah. And additionally, so it also has Gaga theorems for this analytic space. So if you have so all the things that you're used to from complex to non-Archimedean, complex to algebraic geometry, many of the things will still hold. But what you gain, okay, so this so far hasn't told you much. So X analytic is locally compact, path connected, and then X analytic is Hausdorff if and only if X is separated. So it sees the scheme theory of X, the sort of topological aspects of the scheme theory of X. It's compact if and only X is proper. It's just generally very nice. Yeah. So this is has the topological type, at least in certainly with the fields that I said. These are theorems, these are expected in general, as topological type of a finite simplistic complex. Homotopy type.
So, I'm sorry, so an open set in A1 of spec C or whatever, around the middle point.
In A1 analytic.
Yeah.
Yeah, so it will contain, okay, switching back to my yellow. So along finitely many of these branches, it will contain certain radii. Okay? And then along all the other branches, it will contain the whole branch. So there's that co-finiteness. It comes down to the fact that polynomials only have finite many roots. So I can only sort of I can throw out only finite portions. And then so this is an open set.
What indexes the set of these rays? The set of these rays
is indexed by the residue field of the field that you work with.
So the complex part.
So in this case, the complex numbers.
The affine line or the projective line?
And the projective line here. Yeah. So they're places on the function field. Think about them now. So they're points on the smooth projective model.
So it's P1, so it's CP1?
Yeah.
Or RP1?
CP1.
CP1, but one direction is distinguished. It's not a homogeneous.
Yeah, so one direction is distinguished. Sorry, I meant to draw a little dot there. So there's one point that's deleted, but that point is only deleted at infinity. So P1 analytic looks the same, except you plug in the hole. Yeah. So A1 analytic and P1 analytic are still only one point apart. They're not a whole ray apart.
So on every other ray?
Yes. Yeah, every
the
other
ray
ray
itself looks like what?
R union infinity. So this is R union, oh, sorry, R positive
It's
union.
a closed interval.
Hmm?
So it's just a closed interval.
Yes. Yes. But it actually has a
But the length
canonically defined
matters.
metric.
The length.
Yeah. It has a canonically defined metric. But topologically, yeah. It's a closed interval. All right. Cool. Okay, so that's my. Oof, I'm gonna have to get my way. All right. Let me tell you about tropicalization.
Not to derail you, but nothing of what you said is really limited to schemes, right? I can do it with algebraic spaces.
Yeah, of course. You can do this for Arkenstacks now. Yeah, in fact, that will play a role later on. Yeah, so nothing is, yeah, until a year ago, every time I meant to say scheme, I said variety, and now every time I mean to say Arkenstack, I say scheme. I'm young, you know. It takes me time to learn these things. Okay. So, the most traditional version of tropicalization starts off with an algebraic torus. So, M is the character lattice of the algebraic torus. I take its group ring. I take spectrum of that. What is the point of having this here? Is that I have explicit coordinates on the torus. Right? So that's the whole. So this is just like a theme to keep in mind. So every time I have a point of the Berkovich analytification, what is this? Well, this is a map from the coordinate ring to the extended real numbers. But sitting inside this coordinate ring is a distinguished monoid of a distinguished group of functions, which is the characters. Okay, so I can restrict to the characters, and I lose a lot of information this way, right? I only know what happens to monomials. Ooh, T. But nonetheless, what I get is a homomorphism in groups from M to R. This is a co-character vector space, if you like. Isomorphic to NR if you learn your toric varieties from Fulton's book. Okay, but what's the point? It's isomorphic to some vector space. Okay, so this is a continuous map.
Sorry,
And, yeah.
Is it allowed to go to infinity or not?
So if you think about, so this,
Oh, it's a group one, isn't it?
yeah,
I mean,
yeah.
but could you not send everything to infinity?
No, yeah, M are invertible functions.
Pardon?
The functions in M are invertible. So if one of them has size infinity, then the inverse has size negative infinity, which doesn't make sense. So, yep. Yeah, so, yeah, I could have written union infinity. Just would have been the same thing. Okay. Good. Okay, so this is the first immediate advantage of seeing, that we see of taking Berkovich analytification, is that the source has a topology with respect to which the tropicalization is continuous. I should say that analytification is functorial. So I get morphisms for free, I get, yeah, okay. So in particular, if I have a subvariety of my torus, then I get an analytification of that subvariety and a map onto Rn, and this thing is called tropicalization. So this is one version of tropicalization. Okay, so what are some basic properties of trop X? Trop X or trop Xn? Well, it's a polyhedral complex. So this is a polyhedral complex. Polyhedral complex in Rn. It's actually a rational polyhedral complex. Rational with respect to the value group. So this explains, and then the dimension of that polyhedral complex is the algebraic dimension of X itself. So it remembers something. Whatever this process is, it remembers something about the variety. It turns out it remembers a heck of a lot more as well. So remembers at least the dimension. That's an important invariant if you're at least getting your feet off the ground. Remembers the dimension of the variety. Okay. So I'll make two quick comments about this. Okay, I'll say one comment and I'll write down two others. Yikes.
How do you define the dimension of the negative space?
So I have not written, so this is polyhedral complex in Rn of dimension equal to the dimension of
Yeah,
X.
so this how about the dimension of the XAN?
So dimension theory for analytic spaces is subtle. Yeah.
But it's for the original scheme, right?
This is
this is
just the
This is
scroll
algebraic.
dimension of the scheme.
This is algebraic. I'm not cutting out X using inequalities.
Just from your picture of that A1C, it's hard to see what the dimension is.
It's 1. Because it's
Archery.
It's because, well, one way to, okay, I shouldn't be,
Never mind.
okay, so you can take it to be the, okay, let me not say anything. So we don't need it for dimension theory is a little bit subtle over non-Archimedean fields. It shouldn't surprise you either because although this field seemed perfectly harmless, if you think about the field being, Puiseux series or something larger than that, the second you have an algebraically closed non-Archimedean field with a non-trivial valuation, its valuation ring is non-Ethereum. So if you try and work through the chapter of Etienne MacDonald where they do dimension theory, and you throw out the Ethereum hypothesis, it's tough going.
Is this some sort of moment map?
Oh, thank you. Looking at my notes. Good. All right. So let me say that. So first of all, if I replace T by a toric variety, nothing really changes, right? I can stratify T into torus orbits, and then what are the torus orbits? They're quotients of the torus that I started with. So I can tropicalize them, and they will be, you have to believe some commutative diagram here, they will be quotients of this vector space by some subspace. And then what you get, the tropicalization of a toric variety in X delta is a compactified vector space, which I'll denote N delta. Okay? And this is, if I have, okay, so if I'm in a situation where moment max makes sense, if I'm a smooth toric manifold, for instance, then N delta is a polytope, is a polyhedron that's combinatorially, it's not the same, but polyhedron that's combinatorially isomorphic to the polytope. So where moment map makes sense. Well, yeah, so no, where the polytope makes sense. So this is projected. Okay, but there's a better way. There's a better way yet. So this is a new perspective. Some framework and a theorem, a very nice theorem due to Martin Ulrich. So here I have my analytic space. Now here's something I can do. I can take my analytic space, and I have this dense torus, and you ought to believe that an analytic group, that's an algebraic group, so if I analytify that, I should get an analytic group, whatever that is, in this category that I haven't told you much more about. It should be an analytic group. And what you gain when you go from thinking about C star as being an algebraic group to thinking about it as an analytic object, well, you can say what it means to have norm 1. Right? So the compact torus makes sense now. So T analytic, not, which is my notation for essentially the circle group, I can take a quotient by that as a stack, as an analytic stack. Okay? So the lack of good notion of analytic stack is a lot of the work that Martin had to do to prove this theorem. But thankfully, it is settled now. Okay, what was the point of saying this? Well, this thing, X and mod T and naught, the stack, has an underlying topological space, has a well-defined underlying topological space that is canonically homeomorphic to N delta. then everything that you expect from moment map is true, right? Because the fibers of this are compact analytic tori. Like just the way that a toric variety breaks up, its topology breaks up over the moment polytope, over faces of the moment polytope as tori of various dimension, compact tori of various dimension. The same thing happens non-Archimedean analytically. I'll just say T analytic knot is contractible. Okay? Actually, it's very useful. It's very useful. It's just some like non-Archimedean thing. Okay, but I'm still a far cry from where I wanted to go, because I wanted to study moduli spaces of curves mapping to toric varieties. And even if I took my toric variety to be a point, once I let the genus be at least 2, I'm not going to embed that in a torus. There's not sufficiently many. Right? Once a genus is at least 3 or 4, I think there's a proper curve in there. So there's no way you're embedding it into a torus. Modular space of curves does not embed into a torus. So what does tropicalization even mean in that setting? Okay, so let me tell you how this works. Here's a much more general setting. Let's take a simple normal crossing pair. And from now on, I'm going to, at least for now, let me say I'm working over the trivial valuation. So my variety looks like this. The divisor looks like this. Good. So everywhere locally, I have a model of this as a toric variety. It's not a deep theorem. But here, I have distinguished coordinates. So this sort of looks like A2. Here, I have the distinguished coordinate and everything else seems to be invertible off the boundary. So this is A1 cross GM. And here, it sort of just looks like GM squared. Okay, so I'm not going to get into too much about how one does this, but you can take the tropicalizations of each of these pieces and glue them in a well-defined way. So this produces a map from X analytic, and how this fits in with this picture is very interesting, but I don't think I'll have time to get into it. X analytic maps onto what's called the skeleton of X, and I'm sticking the divisor D there because it depends on the choice of D. Okay, so this is called the skeleton. And this is lots of things, among other.
What is the skeleton?
Yeah, so basically you move over the strata of your divisor. And locally you see a toric model, when you see an affine space of a model. So you take the cone of that affine space. You just take the orthid associated to that affine space, and then basically you make a huge diagram of those cones, and you glue them how the strata are glued. You get a cone complex this way. So it's like a fan, it's just not embeddable canonically into a vector space. Okay. Now this might seem arbitrary, you are losing a lot of information, but okay, so this is called P. P is a strong deformation retraction. It's a nice topological consequence. So in particular, at least once you...
Sorry, how big is sigma? Is it the skeleton? Is it like
Yeah, so if I took D to be empty, it would be a point. So it can be very small. But it's something.
So P is a strong deformation retract.
Right, so if you can find retraction of X analytic.
Oh, deformation retracts onto the skeleton. Okay.
Yes.
Okay.
Yeah, so okay, then I've cheated, right? I didn't tell you how to put it back in there, but there's a canonical section now. Unique continuous section. Okay, so this knocks out a whole bunch of moduli spaces immediately. So this observation was used by Abramovich, Caporaso, and Sam Hain. Okay, so they studied Abramovich, Caporaso, advisor. There was work in this direction, very important work in this direction by 3A as well. Okay, so what is a tropical curve? An abstract tropical curve is just to take a dual graph of a stable n-marked curve and put lengths on the edges. Okay? So these are parameterized by something that looks a lot like a cone complex. It's essentially a fan, some compactified fan. So they show that this functorially coincides with the map P there for the natural boundary advisor. Okay, so there's things I'm not saying, of course, right? Because the boundary of MGN bar is not simple normal crossing, it's normal crossings. So you have to take an étal cover to make it normal crossings and then take a quotient or take a co-limit. And then again, this is a stack, it's not a scheme, and certainly it's only stacked theoretically normal crossings. What does that mean? Well, it means the same thing. You still have to take an étal cover and then it becomes scheme theoretically normal crossing. But there's something to check. There's diagrams that have to be proved to commute, but they do. So at least if you believe in morality, this tells you that the moduli space of tropical curves is the tropicalization of the moduli space of curves. So that's a start. Right? You're not going to get much numerative geometry mileage out of this, but it's a start. So this was inspiration. So this is joint work in 2014 with Cavalieri and Martvig. When we basically wanted to see if we could use this to try and recover correspondence theorems for Hurwitz numbers as a baby case. Turns out that the obvious statement is false. The moduli space of Hurwitz covers, of tropical Hurwitz covers, is not the natural skeleton of the moduli space of algebraic Hurwitz covers. But so this plus some waterfall chromosome theory yields functorial correspondence theorems. Okay, 10 minutes. Okay. So now, this gave us some hope, but still I'm a ways off from. Okay, okay, maybe I should say, what do I mean by functorial correspondence theorem? I mean that because there is a tight relationship, not the same relationship, but a very tight relationship between a particular compactification of the Hurwitz space and a particular version of the tropical Hurwitz space, one can use non-Archimedean analytic techniques. You can use the structure sheaf on the analytic space to prove your correspondence theorems functorially. Right? So very, very, very transparent proofs that are sort of one-liners once you have this kind of statement. So you can extract invariance. That's the sort of main contribution of this work. And there are other versions of functorial tropicalization for moduli space, for Hurwitz, for things like Hassett spaces and things like that. But what's fun is when you can extract some. What's fun for me is when you can start extracting some geometry from this. But again, like I said, we're far away from where I want to be. And I want to get to higher dimensional target varieties. Higher dimensional target varieties. So the question is, what do tropical stable maps encode? Like, let's go back to gamma sitting inside Rn. Like, this is some piecewise linear, one-dimensional graph embedded in a vector space. What is this encoding? It's decorated with all sorts of numbers. It has a balancing condition, so on and so forth. So what is such things encode? There's lots of answers to this based on who you ask, because each one of those proofs that I said has a different perspective, and they're quite different from each other, so the answers are quite different from each other as well. Some more different than others, of course. So the answer, being a really satisfying answer, I mean, okay, this is obviously my perspective again. So I'm just adding to the list of different answers you can get to this question, but this one seems to unify it. So remember, so recall, we're fixing the contact order. Order of contact for our curves. Right? So I have something like this. Here's my characterizing. And I have transverse contact there. Maybe a couple of tendencies, something like that. Okay. So the second you start in families, the second you start imposing contact order conditions, you immediately observe two things. First, you observe that you no longer have a proper, no longer clear how to compactify your moduli space. Right? Why? Because two transversal contacts can come together and form a tangency in a family. Right? And then that's not allowed. I just threw that out by putting that condition down. And secondly, the deformation theory is completely unclear as well. Not completely unclear, so somewhat unclear. Deformation theory is unclear. Why? Well, for the opposite of the reason as before. If I have a second order tangency in a family, I can smooth that out into two transverse contacts. Okay. So now, in order to motivate log geometry in 5 minutes, what to do? Okay, I'll do it anyway. Okay. So what does contact order even look like? I have a curve, and let's just ignore the other boundary divisors for a moment, and its tangent. It's tangent at P to this divisor D. What does that mean? Well, it means the following annoyingly complicated way of saying a simple thing. Well, locally in X, locally near this point in X, I have a function cutting out D. Right? If I take powers of that function, I get a monoid, the natural numbers. Right? Get the natural numbers, and I'll just stick D as a copy to remember that it's there. D as a subscript rather. And then I can pull back functions. And then I get, in a neighborhood of P, I have a parameter P, a parameter T cutting out P inside this curve C. So, and what does contact order 5 mean? It means that this map is multiplication by 5. Contact order E means multiplication by 5. Okay, good. So this is all superfluous information in the scheme theoretic case when you're transverse, or transverse up to the point that you want. But it would be really great. I mean, okay, well, the problem arises when this curve falls into the boundary divisor, right? Because once it's into the boundary divisor, I can't tell what tangency means. So it would be great to have a world in which D carries this monoid along all the time, P carries this monoid along all the time, and a morphism in this world, a morphism in this category, just means that you in addition to pulling back functions, you also have to pull back the monoids that are these distinguished functions, like the ones that cut out D. So this is the idea behind Gromov-Witten theory, behind log Gromov-Witten theory. This is Siebert's, this is the insight that Siebert had in 2001. Many years later, we now have a full theory. Okay, so what is the log scheme? The log scheme is a scheme X with a sheaf Mx of monoids and a map alpha from Mx to Ox. Okay, so what is Mx? It's a collection of distinguished functions. So I want to tell you how to think about an element of a monoid as a function. Right? So 3 in here should be thought of as T cubed. And that's what this map is telling you. And additionally, what is t and what is the function cutting out d? They're the functions that become invertible once I throw out the boundary. It's a tautological thing to say. Cut out the boundary, so when I throw it out, it becomes invertible. And so mx is, sometimes people like to think about it as nearly invertible functions, nearly with respect to some boundary divisor. So just by like morality and English, everything that's invertible should be nearly invertible. So alpha inverse of OX star to OX star. This is an isomorphism. Okay. So now you have objects. How do you define a morphism in this category? Well, it's a morphism of schemes such that I gave you some distinguished functions, and I want distinguished functions to pull back to distinguished functions. So they're great. There's a category of them. And the most important result from our perspective is that the moduli space of logarithmic stable maps, stable means the same thing as it used to in Gromov-Witten theory. So your usual conditions on contracted genus zero analytic components. Logarithmic stable maps to a logarithmic scheme, smooth logarithmic scheme, this is proper. Once you fit the discrete data, it's proper in finite time. So this is the main theorem of Abramovich, Chen, Gross, and Siebert. There's a slash there. Separate. Okay, so all of which is to say, what do log stable maps encode? No, sorry, what do tropical curves encode? Now there's an association to every tropical stable map. This is the construction that starts to eliminate things. To every tropical stable map, there's a one-parameter family of maps C gamma over spec C double bracket are positive, so a little non-Noetherian disk. Just because I can make this as large as I want. Take this to be the formal power series if you want. To x. And we're fixing x. Fix x equals x delta throughout.
You mean t to the power r positive? It's the Novikov field.
Well, okay, yeah.
Ring.
Sure. Either. Okay. So, no, my apologies. This is false. Not to x, but to x mod t. This time. Okay? You can't map to x for the same reason that the virtual fundamental class is a thing in Gromov-Witten theory. Because there are families of logarithmic stable maps that have higher dimensional obstruction spaces than you expect, and there are families of tropical stable maps that have higher dimensional and tropical obstruction spaces than you'd expect, but they match up rather beautifully. Okay, so theorem. And with this. So I wanted to give you a functorial tropicalization for logarithmic stable maps to a toric variety. So let me say L sub gamma of x. Logarithmic stable maps, gamma is just my, let's say L of x. I'm fixing the discrete data. Okay? L of x, fixed discrete data. Given any one of these, I can compose with the quotient map to get this map to a stack. And now, this, right, so this satisfies Murphy's law. In algebraic geometry, Rabi kills Murphy's law in algebraic geometry. Right? So any singularity you can come up with will show up in one of these spaces. So getting local monomial coordinates, like, oh, a simple normal crossing divisor, yeah, no, good luck with that. This is a logarithmically smooth, take it to the SNC pair, Hartenstein, admittedly of infinite type. That's not a huge headache. Now, I'll point out one thing I won't say as part of the theorem. this thing carries a virtual fundamental class. The virtual fundamental class is constructed for the relative perfect obstruction theory coming from this map. So that means something to you, great. If not, ignore it. But the point is that this has a good tropicalization, and this, now encoded by this map is telling you all the combinatorial data that you could possibly want to know about tropical curves, about logarithmic stable maps, which are tropical curves. The combinatorial data is tropical curves. So this furnishes a combinatorial tropicalization for L of x analytic, meaning a sort of projection to the skeleton. And then there's lots of corollaries, which I don't have time to say, including like one-line proofs of all known correspondence theorems in tropical geometry, and a sort of tropical Murphy's law, which says that the question of which tropical curves come from maps to toric varieties and which don't is A, a polyhedral condition, and B, an arbitrarily complicated polyhedral condition. It's like a tropical Hilbert 16th problem. And that's a good time to stop. Thank you. Sorry for
Thank you. Questions?
Yeah.
Say again, the LX is a moduli space
Yeah.
of log stable curves.
Logarithmic stable map. So this is.
And the L of the step is on the other side. The L of the step.
Yeah. Okay. So this is log stable maps to a toric variety x delta. This thing is pre-stable map.
With respect to what boundary? Do you take the full toric boundary or?
Yeah, so
or
when I say toric variety, I mean with its canonical toric log structure. And this one is pre-stable maps to x mod t. So this is a logarithmic Artin stack, logarithmically smooth Artin stack. Very easy to see that actually because it has a canonical covering by x. So this is logarithmically smooth, and it makes sense to talk about logarithmic stable maps to x mod t. And so let me, okay, so why on earth would you expect this to help? Toric varieties, so okay, obstruction theories are controlled by H1 on the source curve of the pullback of the tangent bundle if you're in usual Gromov-Witten theory, right? So this is why genus zero curves to projective space are nice, or the log tangent bundle when you're in log Gromov-Witten theory. Now toric varieties, so it's a simple calculation. What do I want to say? The log tangent bundle of a toric variety is trivial. It's OX to the dim x. It's logarithmically smooth. But x mod t behaves like a toric variety of dimension 0. So it's OX to the dim x, but dim x is 0. Right? So this is zero-dimensional Artin stack. So this group vanishes for x equals, well, intuitively at least, h1c f star t x mod t log. The thing is 0 because the sheaf is 0. And so that's why this becomes logarithmically smooth. And so it's sort of like putting your horrible face.
No, but it's not only logarithmically smooth. What you're saying is that it behaves like a discrete object. So if you tropicalize it, you're just doing, if you just want to count the part that's coming from the tropicalization, you're just doing straightforward counting rather than.
Well, no, this has polyhedral, this thing has sort of polyhedral moduli.
Yes.
So it's an.
But then it's just the Euler characteristic of the polyhedron, the counting, or not?
No, it's not.
So what is it?
So in the nice cases where the cases that I listed, what ends up happening is that you can identify the local structure of the space of logarithmic stable maps with the local structure of the space of logarithmic pre-stable maps to this Artin fan. To this Artin stack. Right? And once you've done that identification, what you're trying to calculate is the degree of some evaluation morphism.
Yes.
And you do that analytically.
Yes.
And the analytic calculation here ends up becoming an analytic calculation here because you can compute the degree of the evaluation morphism anywhere you want, algebraically or analytically. So you get these things for free. Sorry, that's an extremely messy statement of the main theorem.
Sorry, maybe
Yeah.
I may misunderstand you.
Okay.
On the left-hand side, usually you need to do a virtual counting on
Yeah.
X. Now on your right-hand side, do you still need to do virtual counting or?
You can't count here. You can't count here. So this is a way of understanding what tropicalization is doing functorially. So here, so you'll notice in every one of the situations that I wrote down, there was no virtual. Right? These were algebraic counts equal to tropical counts. So one of two things is happening. Either the moduli space of logarithmic stable maps was smooth, or the excess dimensional components didn't contribute. So this is the case when you have higher genus maps to toric surfaces. So how exactly the virtual fundamental class on this interacts with tropical curve counting is the degeneration formula, which is at this point not known in logarithmic geometry. The point of this statement is that it's telling you what ought to be true in those cases. When you actually, when you genuinely have a virtual fundamental class, then it's telling you that tropical, it's giving you a functorial reason why tropical curves are still going to index the degeneration formula.
Okay, but can you explain like in the tropical counting, you still have the superabundance problem as the moduli space of the tropical curve is bigger than your
Yeah. So yeah.
Solve the problem.
No, well, you can't solve that problem because you're trying to do algebraic curve counting, right? So you're going to see the problem somewhere. What this is telling you is that superabundance is the same thing as having excess dimensional components in the moduli space of maps, right? A priori, that's just some coincidence that whenever you have superabundance on the tropical side, you have large dimensional components on the classical side. Why does that happen? Right? It's not clear that the classical statement implies the tropical statement, or vice versa. And this tells you both, actually.
This tells you when you have the superabundance phenomenon, then you must have obstruction on.
That's right. That's right. Yeah, so the entire, it turns out that at least near the very degenerate loci of maps, the obstruction theory becomes combinatorial. So the obstruction theory for log stable maps acquires, like the cohomology groups acquire coordinates, and you can write them down in terms of tropical deformation and obstruction theory.
Yeah, so somehow the punchline of this theorem is that it converts information about the obstruction theory on the logarithmic side to tropical information.
Exactly. So it tells you how to do the combinatorial part of the obstruction theory classically.
But you can still have obstruction theory information vertically in the fibers, which you have to separately analyze.
Yes, exactly, right. So
it just captures the combinatorial part of the obstruction theory, and then you still have to analyze.
So it's giving you reasons for why superabundance is related to non-trivial obstruction groups classically.
So superabundance is like the quotient of the obstruction theory on the other side.
Maybe. I'd have to think.
No, it's just saying, it behaves like whatever complications you have combinatorially plus some smooth part which could still be non-trivial.
That's right.
The fibers have a well-defined perfect obstruction theory. It can still be non-trivial, it can contribute, but all the complexity that's not smoothly behaving, it's in the combinatorial part, and it tells you exactly how it is related to it.
So for instance, if you took X to have trivial log structure, okay, so I said all of this for X being toric. You can replace X with any logarithmically smooth thing, but then this is not X mod T, it's some other zero-dimensional Arnstadt. It's called the Arnstadt of X. If you were to take the trivial log structure here, you'd recover usual Gromov-Witten theory. But then this would be trivial. This would then become trivial. And so that's still happening, except it's happening sort of Yeah, that phenomena is happening as the source curve degenerates in various ways.
More questions? Well, let's thank Dhruv again.